At the end of the lesson, you are expected to identify the building blocks of gradient-based optimization, develop foundational skills for gradient-based optimization, and appreciate the essence of optimization for deep learning. Before we start, be sure to click the subscribe button for more updates of our data science lessons. So let me start by saying that gradient descent is a repetitive process that takes us to the minimum. So I'm so sure you are familiarized already with minimum. So this minimum can be a global minimum or a local minimum. So depending upon the situation. So you may study lesson 18.1 to know more about what global minimum and local minimum because these concepts are very important in this lesson. So the link to 18.1, lesson 18.1 is given in the description below. So although we can say that gradient descent is only for continuous spaces, let me write continuous. Okay, let's see this part. So continuous. So when we say continuous spaces, it has something to do with continuous variables. Okay. So we've been talking about continuous variables and then discrete variables. So we have lessons on that. Please check my lessons on machine learning because these are very basic concepts for us to be able to build our foundations in learning both machine learning and deep learning. Okay. So the use of iteration for a small move, and hopefully this is the best small move. So to a better configuration that can be generalized for discrete spaces. So this formula, this one provides the totality of the concepts of the concept of gradient descent. So you can see here different entries or elements of the formula, and I believe that you would like to ask me this very beautiful question as of this moment. So you would like to say, or you would like to ask, what does each of these elements mean? So let's start with this one, the theta prime, which is the next position, and this is the one that we hope to get to arrive at our destination. So in short, this is our main target, the value that we would like to get. Okay, then we have here the theta to the power 0. What does it mean? So this is our current or present position. So for example, do you remember this bowl shape? So our current situation is this and this on the right. So these two positions are this, okay? And then we can also see this one. So what does this mean? So this is actually the opposite position, which could be right or it could be left. Okay. Then what about the alpha? What's the meaning of this? So this one means the small steps that we will take. And what about this one? This is actually the symbol for gradient descent or gradient. So this is the direction where we could have the fastest increase, this one. So after knowing these entries, the next question to answer is, how do we arrive at this mathematical expression? So we will have them one by one, and we're going to use linear regression just for simplicity and better understanding of the lesson, so we could easily understand some of the, at least for now, the concepts. Okay, but we're going to lay down first the foundational concepts that we're going to use for the gradient-based optimization. But of course, as we go along with our discussions, we will be learning more about the different algorithms. Okay, not only linear model or linear regression. So let's consider the amount of data in a 2-day space. Okay, so we have here a 2-day space. So for example, this data is about sales revenue in relation to customer demographics. Okay, so here we would like to predict the kind of relationship between sales revenue and the customer demographics. Okay, so given this predicted relationship, we would be able to predict the amount of our sales revenue And in the context of machine learning, this is a supervised technique. So if we are going to draw a line to arbitrarily describe our data, it may look like this. So we have here a straight line, a very good line to describe that our revenue is increasing. Okay, so here it stands for our demographic, the demographics of our customers, and here the y-axis that represents the revenue that we've got for, shall we say, a number of years. Okay, so I believe that you've already known that this illustration represents a simple linear regression. So with this equation, y equals mx plus b. So we know that m, let me underline this. Okay, m is the slope, which is the change in y with respect to the change in x. And here is b, and b is the intercept on the y-axis, as you could see here. So this is the point where x and y intercept. So this model will give us predicted values given the new set of inputs. So basic to this idea is the concept of error. Okay, so we have your error, which is the difference between the predicted value of y, or what we call the y prime, or in some cases you could also see the y hat, okay, and the actual value of y. So this is the formula. So we have error, which is equal to the predicted value, or the y prime, minus the actual value of y. So we say that the less error, the better, as this is close to reality. So this concept of less error is very much related to the idea of loss function or cost function. So let's talk about cost function. What is it all about? I think I have to write here, cost function. Okay, here. Cost function and then the loss function. So let's describe the relationship between loss function and the cost function. So while loss function, this one, computes the error for a single training, cost function measures the average of the loss function for all the training examples. So in short, just the name itself, it takes only one data for us to be able to identify the loss, the amount of loss. But in the average, or in the cost function, we need lots of data or training examples for us to be able to arrive at the average loss. Okay, so no-brainer, simple concepts. So this function, the cost function, evaluates the performance of our deep learning algorithm. So whether it is good or bad in making predictions for certain values of m and b. So we have this formula in computing the cost function. So we have cost is equal to 1 over n. Then we have here the sigma function, which represents the summation of the difference between the predicted value of y and the actual value. Then we square that. Okay, the summation of the summation of, let me repeat that, we have here the summation of the squared difference of the predicted value and the actual value. Okay, so I am sure you are asking yourself why we need to square the difference. So why are we not going to use the absolute difference? Is absolute difference not acceptable if we are talking about the cost function, right? So just very nice questions to talk and to answer. So the answer is, this makes it easier to get a regression. So to do this, we need to compute for the first derivative of the cost function. So if the absolute difference is used, it is much harder to do this. So to find proof, you may do it yourself and then just play around with it, and then of course you can make justifications. Okay, so we don't need to go further for computing for the derivative. In our next lesson, we will have that. Okay, so but I suggest you review your lessons on finding the derivative. So one more thing about derivative, it is useful for minimizing a function because it tells us how to change x in order to make a small improvement in the case of y. Okay? So the goal of any machine learning algorithm or deep learning algorithm is to minimize the cost function. So the reason for this minimization is that a lower difference between the predicted value and the actual value would mean that a certain algorithm, as far as a certain set of data is concerned, has done a really good job. So if not the best for exceptional cases. So the most interesting question at this point would be how do we really minimize any function? So our cost function is of the form y. Okay, we have y equals x squared. So let's consider this Cartesian coordinate which has a parabola, and this illustration or graphical representation represents y equals x squared. So we have here a parabola. So to minimize this function, we have this function. We're going to identify a certain value of x that can produce the lowest value of y. So for example, we have here of course we have different values of x. Okay, now what we're going to do is that we're going to find the least value of x so that we can arrive at the lowest value of y, and the lowest value of y here is found here. Okay, so again, this is the lowest value of y, and this is the global minimum if we have, in some cases, if we have lots of local minima. This lesson provides prerequisite concepts that help us navigate our way through understanding and mastering gradient-based optimization. These concepts are applicable in a lot of machine learning and deep learning techniques. But again, for the sake of simplicity, we use a linear model. So as we progress with our course, we will bring other algorithms wherein we are going to also use gradient-based optimization. After all being said and done, let's try this. What is the concept of cost function? How is it different from loss function? How do we minimize a function? And why do we need to understand the foundational concepts of gradient descent? Leave your answers in the comment below so we could discuss properly and our interaction would become lively and you and I can learn from each other. Do not forget to subscribe, like, and share. Please click the bell button to be notified every time we have a new session. See you in the next lesson.